Hello and welcome. In this video, we're going to continue to take a look at series and determine when they converge and when they diverge. Now, we've taken a look at a few specific series already in previous videos that are going to be really useful to compare with. We've seen the geometric series. We know when it converges. Better yet, we can actually calculate its sum directly using a formula whenever it does converge. We've also seen the harmonic series, which is divergent. And we've seen p-series, and those are sometimes convergent, but we don't always know their sums. We can't necessarily calculate them with a nice easy formula. In this video, we're going to be taking a look at various different series that are probably sort of similar to those kinds already, but just slightly different. Something that you wouldn't be able to say is exactly a geometric, harmonic, or p-series. So we're going to do a comparison with what we have as a given series and one of those ones that we're already familiar with. So it's called the comparison test. And we've got a couple different comparison tests that we can use. Let's start off with just the comparison test. And here we're going to have two series that we're comparing with. So to distinguish between the two of them, we'll call the terms in one series AN, and that's typically the series that we're starting off with. And we'll call the terms in the other series BN, and that's typically a series that we're already familiar with. Both of these series need to have positive terms though. Now the first conclusion that we can make is if the series BN is convergent, and every term in our other series AN has smaller terms, or AN being less than or equal to BN, then the smaller series is also convergent. And hopefully that kind of makes sense. Convergent would definitely imply that we have a finite sum, and being smaller than a finite sum means that, well, our sum is also finite. Hopefully the other one makes sense as well. Our second conclusion is that if the series with BNs is divergent, and all of the AN terms are greater than or equal to the BN terms, then the other series with AN must also be divergent. Those are the only two kind of conclusions we can come up with on that comparison test. And we'll see some examples in a moment, but I'll also just give you this other test called the limit comparison test, which is very similar. We're comparing two different series, and typically the terms in one are labeled A and the terms in the other are labeled B. Typically the series with A's is what we're looking to try to analyze, and the series with B's is a series we're familiar with. In this case, though, we actually form a ratio of our AN term over a BN term. So they're corresponding terms, but we're looking at the ratio AN over BN. We take the limit as n goes to infinity, and if that limit exists and it's a finite number, with it being greater than 0, then either both series must converge or both series must diverge. And since we'll be comparing to a well-known series that we know converges or diverges, then we can make the appropriate conclusion about ANs. Now let's try both of these in practice with series that look kind of similar to geometric, harmonic, or p-series. Let's take a look at a series from n equals 1 to infinity of an expression 2 to the power n over 3 to the n plus 1. Now there's a couple things you can always take a look at first and see whether or not you think this is going to diverge or converge before we get too far. For instance, what happens as n goes to infinity? Are these terms getting smaller, closer to 0? Well, in the numerator we have 2 to the power n, but in the denominator we have 3 to the power n. The denominator is certainly getting much larger than the numerator, so it does seem like each term is eventually getting closer to 0. So the test for divergence isn't telling us that it diverges anyways. But after that, it may not quite look like it, but it's fairly similar to a geometric series. So why don't we try the comparison test? We have to make sure that we start off by knowing that all of the terms here are positive, which of course they are. So let's compare this by taking a look at something that is as similar as possible. If we call our terms AN, then AN, the nth term in our series, is 2 to the power n over 3 to the n plus 1. It's fairly close to a geometric series with the exception of that plus 1, which actually is pretty insignificant when n gets very large. So why don't we try making a comparison? We'll compare that to this expression, 2 to the power n over 3 to the power n. And we're not looking for an equation, we're looking for an inequality. We're trying to come up with either a less than or greater than symbol to compare these two quantities. Well, I know that any fraction with a larger denominator is actually going to be smaller than a fraction with a smaller denominator. So we know that an is going to be less than 2 to the n over 3 to the n. And over here, if I just want to simplify, I can use equal signs and make this maybe 2/3 to the n. Or even better, I could make this 2/3 times 2/3 to the n minus 1. Now, if I construct a series with that as its expression for each term, we'll have a geometric series. The geometric series, 2/3 times 2/3 to the n minus 1 from n equals 1 to infinity, is convergent because r, our common ratio, has an absolute value that is less than 1. Our r in this case is 2/3. And by the comparison test, the nth term in my series, an, is less than the nth term in the convergent geometric series, so I must also have a convergent series. The comparison test works in that case because I am smaller than something that's convergent. If I was larger than a convergent series, then, well, I wouldn't be able to make any kind of conclusion. It doesn't tell me that I actually have a finite result or not. So be careful. Let's try another example and see if we can make another easy comparison. Let's look at the series 2n minus 1 over n cubed plus 3 from n equals 1 to infinity. Now, it doesn't look like I could compare this to a geometric series because, well, there's no kind of expression where we have a constant to a power n or to the power n minus 1. So it's probably better to try to compare this to some other kind of series where we have powers of n in the denominator. That would be like a p series. Let's see if we can make a series of comparisons with less thans or greater than or equal to symbols and see if the comparison test will give us a meaningful result. We'll start by labeling the nth term in our series as an, and that is 2n minus 1 over n cubed plus 3. And to make this look closer and closer to a p series, let's take out one of the two terms in the numerator. Let's get rid of this minus 1. Okay, well that is essentially like we're just adding 1 to the numerator. Will that make the fraction on the right larger or smaller? Well, that makes the expression on the right larger. So we can put in a less than symbol. An is now less than 2n over n cubed plus 3. And we've made our first comparison. But this 2n over n cubed plus 3 is still not any kind of series that we're familiar with just yet. So let's take away this plus 3 in the denominator. That's essentially just subtracting 3 from the denominator, and that will make the new expression on the right slightly larger. So we've made our second comparison. 2n over n cubed is larger than 2n over n cubed plus 3, and since the inequalities all point in the same direction, that also tells us that 2n over n cubed is greater than our original nth term, an. And from here, we can make this look like a p-series because n's cancel. We have 2 times 1 over n squared. Now, if we were to construct a series, the series 2 times 1 over n squared from n equals 1 to infinity can be simplified by taking the constant out of the sigma notation. That leaves us with a convergent p-series since p is equal to 2. Since that is a convergent p-series and following all of the inequalities that point in the same direction, our nth term is less than or equal to bn. That tells us that our given series must also be convergent. All right, well, let's try another example of a series that is fairly close to maybe a p-series or geometric series, but this comparison test maybe doesn't work as intended. Now this series looks a lot like a geometric series, 1 over 2 to the n minus 1 for n equals 1 to infinity. So let's start off the same kind of way. We know that these terms are always going to be positive from n equals 1 to infinity. We would probably want to compare this to the series 1 over 2 to the n. Now if we do that, 1 over 2 to the n minus 1 is going to be a slightly larger fraction than 1 over 2 to the n. Simply because if we have a smaller denominator, it ends up being a larger fraction. Well, that makes a bit of a problem actually. That's because we know that the series 1 over 2 to the n from n equals 1 to infinity is a convergent geometric series since the ratio there is 1/2. But the comparison test doesn't work if we are larger than a convergent series. If we're larger than something that converges to a finite number, It doesn't rule out the possibility that our sum could be infinite. So there's no result from the comparison test just yet, but this is where the limit comparison test might come in handy. In the case of the limit comparison test, we start by forming a ratio of our given series, an in the numerator, and the comparison that we want to make, bn in the denominator. So let's compare our 1 over 2 to the n minus 1 to 1 over 2 to the n, since they're so close to each other. Now, hopefully we can go and do a little bit of manipulating on this expression, simplify it, and evaluate that limit. We can start off, first of all, by taking the reciprocal of the denominator and turning this into multiplication. Well, that gives us 2 to the n over 2 to the n minus 1. When I take the limit as n goes to infinity, there are maybe a couple of tricks that we can use here. We could use L'Hopital rule, or we could multiply numerator and denominator by some non-zero expression that will help simplify. In this case, it might be really handy to multiply numerator and denominator by 2 to the negative n. In the numerator, this gives us 2 to the 0, which is 1. And in the denominator, we have 2 to the 0 minus 2 to the negative n. So that gives us 1 minus 2 to the negative n. And as n goes to infinity, 2 to the negative n goes to 0, and this equals 1. Now that is a positive constant. It's a finite number. So that means that both series either converge or both series must diverge. The good news is that we've picked a series that we already know converges, and that means that both series must converge. So that limit comparison test really helps us to get out of that situation where we have a series with greater terms than a convergent series that we want to compare to. Hopefully the limit comparison test is strong enough that it will help you to handle those kinds of situations. Now, let's take a look at least at one more example of a series that involves kind of an expression that we might not obviously compare to either a geometric or a p-series. In series, we often see n factorials. Now, just a reminder, n factorial is simply an expression where we take n and multiply n by every consecutive positive integer less than n. So that means we have n times n minus 1 times n minus 2 times n minus 3, and we continue to multiply by the next highest integer until we reach the end of the positive integers. So we'll stop when we reach 3 times 2 times 1. We don't multiply by 0 because, well, then n factorial would always equal 0. So really, n factorial, another way to think about it, is the product of the first n positive integers. Now we do make one special little concession here, and that is that 0 factorial is defined to equal 1. But other than that, we have fairly predictable behavior. We have 1 factorial, which is equal to 1, and 2 factorial, which is equal to 2 times 1. 3 factorial, 3 times 2 times 1, and you get the idea. Now, how are we going to try to make a comparison with n factorial to either a p-series, where we have usually n to a power of p in the denominator, or a geometric series, where we typically have a constant raised to a power of n? Well, we can start trying to compare this to a geometric series, although it's not exactly obvious right off the bat. Once we get past 2 factorial, we can make some nice comparisons. 2 factorial, sure, is just equal to 2 times 1. No problem. But let's start making some adjustments for n equals 3 and onward. When n equals 3, 3 times 2 times 1, well, that is greater than 2 times 2 times 1. 4 factorial, 4 times 3 times 2 times 1, that's definitely greater than 2 times 2 times 2 times 1. 5 factorial, that's definitely greater than 2 times 2 times 2 times 2 times 1. So 2 factorial is equal to 2 to the 1. 3 factorial is greater than 2 squared. 4 factorial is greater than 2 cubed. And 5 factorial is greater than 2 to the power 4. In general, n factorial is greater than 2 to the power n minus 1. And that gives us a nice comparison between factorials and geometric series. So let's start off there. We'll start by labeling the terms in our series 1 over n factorial as being equal to an. Now, we know how to compare n factorial to 2 to the n minus 1. It's just a little stretch of trying to compare 1 over n factorial to 1 over 2 to the n minus 1. And remember, if you are taking an inequality and you take the reciprocal of both sides, the inequality has to change direction. So 1 over n factorial is actually less than 1 over 2 to the n minus 1. And that is the perfect thing to compare with because those are the terms of some kind of convergent geometric series. The series 1 over 2 to the n minus 1 from n equals 1 to infinity can be rewritten as the series of 1/2 to the n minus 1 from n equals 1 to infinity, and that's a convergent geometric series with r equal to 1/2. Since our terms an are less than the terms with bn, then our series must also be convergent. And that's just using the direct comparison test. So that series 1 over n factorial is also convergent. And it's worth noting that n factorial, it grows very, very large very, very quickly. It is growing larger than an exponential function. So in general, when we have n factorial in the denominator, there's a good chance that it's convergent unless you start to see some other factorials elsewhere in the expression. Well, with the comparison test, you really have to have a good set of known expressions to kind of compare to. So keep in mind our geometric series, our harmonic series, and our p series. Those are really good examples of things we can easily compare to. You have to try to see whether or not the expression you've got, our an, see whether or not that kind of looks like it has powers. Then you might want to compare it to a p series. If it's got exponentials like 2 to the n or 7 to the n, maybe you can try to compare that to a geometric series. And if you can't make a direct comparison just going in some sort of line with inequalities that work out the right direction, then maybe try that limit comparison test instead. Now, we'll see some more tests in the future that may help us when the terms aren't always positive. But for right now, you can only use these tests for the two series having positive terms only. So stay tuned. Thanks for watching, and I'll see you in the next video.